guys hear me in the back? Yes. Good. Yay. Okay. So welcome back for another Science on Tap.
Hello everyone. So I work at WPU, Shared Research Facilities. We're basically a group of labs that are open for any researcher within the university and out. If you need any tools, we usually have many of them there, and I will be showing some of them that are related to imaging today. And basically imaging of microscopic worlds, which means we will go talk about what usually is considered invisible, basically because we don't see by naked eye. And we use these tools basically to observe cells, viruses, genes, and other materials that are very, very small. The reason why we do this is for us to understand these worlds, these materials, if we are able to predict them, to change them, and even create new materials of those sizes that can be very useful for technology in our society nowadays. And for that, first we need to understand them, and we need to start finding ways of seeing them. So this is a quick review of biological scale here, starting with the diameter of the human hair. Here is the micron symbol that didn't show up in this, sorry for that, but the diameter of the human hair has around 100 microns, and that's a reference that we use a lot during the talk. And below that we have cells, red blood cell around 8-7 microns. Bacteria, proteins, we can go to here DNA, that is few nanometers, and around few nanometers we also have the famous nanoparticles that everybody's talking about. And basically they are 1,000 times smaller than a bacteria. So they're very small. And we need special tools to observe them. So we start very basic, how we see. In terms of light will hit an object, and from the object will hit our eye, and our brain will code that message receiver. So this is how we observe colors. And when the light hits an object, if that object absorbs all the light except for blue, for example, we will observe that object as blue, because only the blue will hit our eye. So the subject that I chose for tonight is a winged cell, a winged seed. Here is the path that the seeds usually do when they fall from the tree. And I basically used this seed and went through many different tools, observing the same sample from different angles, different aspects. And that's what we do in science. We have a team, we are researching, and we try to cover all possible angles to study that subject. And basically we'll start with the optical microscope. I have actually the sample here that I'll pass around later. In terms of the optical microscope, it's not much different. If you check a basic optical microscope, it's not much different than what is discussed about the path of the light to the eye. So we have a light source that will hit your sample. It can pass through. It can basically come from another position, hit the sample, and it has to reach your eye, or a camera, or a detector there. And that way we can collect that information about our subject. The difference is we can put some lenses on the path of the light, and then these lenses basically will expand or reduce, will magnify details of that sample, so we can see beyond what we can see only by naked eye. So here is images in optical microscope of the wing of that seed. And here is a bar. The size is about 1 millimeter. So for those who are not familiar with the metric systems, about 0.04 inches. And the same scale here. Now, with the optical microscope, since we're using we can observe micro-sized details and also observe them in color. And this is one of the tools called fluorescent microscope that we have to study more details of samples. For example, here, now instead of 1,000, we are at 100 microns. So this length here is the length of the human hair, and the thickness of the human hair. And we can see many details like powder particles around here in the veins of this material. And they are about, you divide this in 10, they will be about 10 microns, so the size of a cell, red blood cell. And we can, here we are getting closer to the limit of this optical microscope. But we can get details that we don't see usually just by naked eye. Using basically the same principle of the optical microscope, but with a little bit of twister. We'll talk about the optical profilometer. Another interesting tool that basically will have also the light source hitting the sample, from the sample coming back to a detector. But now the profilometer will basically scan the sample. So we'll create a map of the sample profile. Like if you think about the tips in the old LPs or the laser in the CDs, basically we'll go through the grooves and we'll make a drawing of that surface. And the same seed in a profilometer will look like this. So this is the full wing of that seed. The seed is here. And you can see details. They are mapped in color. We can do that with light. And here there is a scale that gives sense to this color. So the top here is around 600 microns. And it will be the thicker part here, the seed. And when you go towards to the other end of the wing, you'll have sizes that are around the 200 microns. So thickness of human hair. And this is all done with light. And this is another detail of a vein. Now we got a little bit closer, and we can see how the surface is smooth, and that we cannot see usually just by naked eye. And sometimes it's very hard also to detect the smoothness with an optical microscope. So we're mapping here the surface. Now my area is electron microscopy. So it's basically, we'll talk about the microscope, same way as the light microscope, but instead of using light, we'll be using electrons. So quick review, if you remember, this is a representation of the atom. So you divide the material all the way to this little particles that have a nucleus and a cloud of electrons flying around. It's basically very much like a beehive with all the bees outside there. And if you want, for example, to remove electrons from this cloud, you can do that. Same way if you poke this beehive, you can get a very nice group of bees out of their home. Basically, this is what we do in electron microscopy. We want to remove these electrons from those atoms. And instead of having now a light beam in my microscope, I want to have an electron beam. And basically, what I'll do is use a little bit of magnetism for that. So we have magnets, and remember, when you have magnets that are charged at the same, and put them together, they will repel. We have magnets with opposite charges, they will attract. So use the same concept, creating a strong field around the ring here, a magnet, and the electrons will be attracted to that magnet, and we control their passage, just controlling these magnets around, and we created this way a beam of electrons. And this is what we'll use for the electron microscope. Now, why we are interested in using electron microscope? A basic light microscope can observe materials from a few millimeters, few centimeters, all the way down to a few hundreds of nanometers. So we are in the limit of the cells and some organelles inside of the cell. And with the electron microscope, we can go all the way down to an atom. So an atom will be around the size of 1 angstrom. So this will be basically 0.1 nanometer. From 1 centimeter, you can see all the distances. Smaller than a virus. Our nanoparticles usually are here around 1 nanometer, so 10 times smaller than that. So this is the sample that we prepared for the electron microscopy. You'll see that the sample here, oops, is coated. So there's it has a coat of a metal inside. And basically, like the optical microscope, you have light that hits the sample and it will come to your eye. The electron needs to hit the sample and be able to also get out of the sample and hit the detector, the camera. And some samples won't be good conductors. It won't let the electron move inside. So basically, we use some metals to improve that. And biological samples, they are usually non-conductive. They won't let the electrons move. So usually they have special treatment to put them in the microscope. And basically this is how you observe an image in the electron microscope. We call it scanning because like in the profilometer, I'm making a map and I'm observing the surface. So I'm scanning the entire surface. And these are details of the wings of that seed, and the green bar here represents 100 microns, so the thickness of the human hair. Just this last one here, that the green mark represents 10 microns. So this is 10 times the thickness of the human hair, and you can see more details. Now we can see all those particles, those powder-like particles, that are about this size or a little bit smaller. So basically the size of a red blood cell. And the images are black and white, shades of gray, because the electrons won't have color like the light. And the microscope will create a certain contrast, certain difference, tones of gray, so we can observe the details in the image. So this is another detail. Now, with a higher magnification, 100 microns, here 10 microns. 100 microns, I cannot see much detail here, but when I zoom in, I can see here a structure that I couldn't see before. So even working with microscopy, we have to go investigate the sample. We might discover things that we cannot see in certain magnifications, but we have the power to go to higher magnifications. Now, I will show the next slide that has some interesting images of bugs. And I hope nobody will get much disgusted. Somebody will eating. So here are some curious images that we can observe with electron microscope. This is my favorite one. It looks like the alien. Basically, so this is an ant. The bar is 1 millimeter. We can scan it by naked eye. And if you be very gentle and grab an ant and get very close, you maybe can see a little bit of this where the eye and ant is, but you won't be able to see much detail. This bar is 50 microns, so if you divide it by here, you have the size of a blood cell, and basically that's more or less the size of the structures in the eye. And the hair, the hair here will be much smaller than that, so you won't be able to see. I don't have the scale bars of these images, so I can't do much comparison, but this is the image of the head of a marine war. So it's just a thing, it's been discovered around 50 years ago. So basically the new technology allows us to discover this new curious creatures. And this is the head of a larva of blue butterfly. So, as you see here, the image is in color. This is artificially colored. It's the electron microscope won't provide a color, but we can color to look more interesting. Now, why we do this? Besides discovering new words and understanding that better, we can also create new materials. And this is what is called a micro-electromechanical system. It's a type of chip. And you can see here, this bar is 500 microns. This bar is, again, 100 microns, diameter of the human hair. Features here are the size of a red blood cell. They were cut, they were designed inside of the electron microscope. Now, these are materials created, designed, and basically you will find this inside every smartphone. If you have a smartphone, you have one of these types of chips inside there. So that's the information being useful in terms of technology and bringing back to society. And we can also play a little bit, and using the instrument, we can make a series of images, dislocated just slightly, and add color like we saw before, and we can create 3D images. And I want to thank Adrian Brown is here for doing this image for us. And I'll be back to this slide after, and we'll have some 3D glasses passing by so you can check the structure when it comes out of the slide. I'll be back there. And lastly, I want to talk about the difference between two types of electron microscopes. What we call the scanning that maps the surface, and we call box, and the transmission. So transmission, like we saw the optical microscope, you can have the light passing through the sample. In the transmission, that's what we'll do. The electrons will pass through the material and hit the detector. So basically, there's a difference. The scanning electron microscope hits the sample, the electrons will interact and will collect them. The transmission will observe the electrons that are passing through. For that, the specimen has to be very thin. If you have a sample that is too thick, the electrons will always stop it on the way. And this is the type of difference that you observe between these two. These are carbon nanotubes, another material that is getting common nowadays. Basically, tubes, nano-sized, and made of carbon. And here is the bar is 10 microns, so it's a very, very thin hair. And this is the scanning electron microscope. Mapped the surface of a substrate that had many of this. And then when we go to the TEM, we can see the detail of some of them, and you can see how thin they are, and you can separate the walls from the internal part. And in this case, we have a bar that is about 100 nanometers, so way smaller. And here it will be with a much higher magnification. I'm now talking about the 2 nanometers, 20 angstroms. If you reduce this by 20, 1 angstrom is the size of an atom. So what you're observing here is basically an arrangement of atoms in a certain material. The black dots are the representation of the atoms. Basically, the electrons are passing through the sample. When they hit the atom, they cannot come and make a spot in my detector. And when they pass between two atoms, they can come down and make a mark in my detector. So basically, the dark spots here will be where you have an atom in this structure, and you have a projection of that material with the screen, and you can collect a lot of information from this. So basically, this is what we do there, the reason why, and I want to thank everybody, my colleagues at Shared Research Facilities, and I also want to thank Via and the Science and Tech team for having me. Adrian, my girl from chemical department, that helped me with the 3D image, the research docs for some of the materials, and these are the manufacturers of the tools that we have there. So, thank you.
How many electron microscopes do you have?
We have one transmission electron microscope and one scanning electron microscope that can actually do also the lithography. In the same building also there is another scanning electron microscope, but it's from the chemistry department. So they're all located, we're located in engineering. We use a magnet that is designed around where the electrons will pass through, and we can control the magnetic field in there. So when the electrons are coming down, when we are doing all the alignment, basically we're pushing, increasing the fields in one direction and another direction to see if the electrons will pass alignment.
Thank you, Marcela. If you guys still have more questions, I'm sure Marcela will be more than happy to answer. And she also has the samples here, the seed samples she used, so if you want to check it out, they're over here. Thank you guys, everybody, again for coming over, and I'll see you next month.